Go ahead.
Okay, the two topics I want to talk about today. First is, I think it would be a good idea for someone, and that means me really, to bring you up to speed with what's happening in Randall Holmes's proof of the consistency of NF. I'm assuming that if you're part of this audience that you already know a certain amount about NF and perhaps its connection with the TST, the Omega order theory of equality is probably the best way to characterize it. Probably the best way in to Randall's proof of consistency is through Ronald Jensen's proof of the consistency of NFU, which appears in Synthèse many years ago. It's a beautiful paper. I strongly recommend you to read it. In the days when I had to lecture a fourth year course in logic in Cambridge, it was one of the things I would cover because it combines ideas from lots of different areas, and model theoretic ideas, ideas from Ramsey theory and type theory, and provides a really quite unexpected result that Quine's NF with U-Elemente, with atoms, is consistent and quite weak, whereas by 1969 it was known that Quine's NF without atoms, the full version, was quite strong. It proved the axiom of infinity. Now, this is a good place to start because in this paper, there is the idea that Randall Holmes extracted and called tangled type theory, as this definition I've given you on this page here. This idea is it's implicit in Jensen's paper, but Randall actually extracted it and showed how this idea could be used to give a consistency proof for NF. What Holmes actually shows in this paper here is that NF is equally consistent with tangled type theory. The current state of play is that Randall's proof, which is now 10 years old, is being encoded, formalized in lean by, really not so much by Randall himself, he's not really a lean hacker, but by a former student of mine called Skye Welshaw at Cambridge, who has got the bit between his teeth. And I'm hopeful that the proof will be completed within the coming months. Certainly, my plan is that I will produce a revised version of the NF monograph to coincide with Randall and Skye's lean proof hitting the newsstands. It'll be good for the royalties. I think it's months away. They're meeting every week, and I sit on their meetings, and I think I'm hopeful because basically I believe Randall's proof. I'm not in charge of all the details, and it's being retweaked at frequent intervals. But the proof is believable, and Skye has an incentive to get the thing to work, but not least because having your name on a paper like that is a very good career move. But the other thing I want to talk about are the synonymy results in the Quine systems. Now, synonymy as a mathematical phenomenon goes back to, well, the earliest thing I can think of is something in the Skolem Memorial volume of 1965. But let me tell you what synonymous theories are. Two theories are synonymous if they're mutually interpretable up to logical equivalence. Now, there are many notions of equivalence of theories as bi-interpretability, mutual interpretability, and all sorts of stuff. The situation is actually more complicated than you might think. But the particular example, concept that I'm interested in is actually is the strongest, and it's actually quite easy to understand. If two theories are mutually interpretable up to logical equivalence, what do we mean by this? We mean that there's an interpretation of the first theory into the second, and an interpretation of the second theory into the first, such that when you compose the two interpretations, either way round, you get, well, you don't get the identity, but you what happens is that if you take a sentence in one theory, translate it into the other, and then translate it back, you're not guaranteed to get the same sentence, but you're guaranteed to get something that's logically equivalent. So let's have some examples of this. I mean, a nice, straightforward example to start with is the theory of partial orders and the theory of strict partial orders. Now, I can interpret the theory of partial orders and the theory of strict partial orders by sending x less than or equal to y to x less than y and x not equal to y. And I can interpret strict partial orders, the theory of strict partial orders and the theory of partial orders by sending x strictly less than y to x less than or equal to y and x not equal to y. And you notice if you compose those interpretations, you get it'll take a formula for one theory back into itself, or at least back to something that is logically equivalent to what you started with. Now that's a fairly trivial example, and we don't normally think of it as interesting, but it does. From my point of view, it has the useful feature that we don't really think of the partial orders and strict partial orders as being different things. We think that they're, as it were, two aspects of the same mathematics. So that the difference between the theory of partial orders and the theory of strict partial orders is really a presentational one rather than a mathematical one. A more familiar and less trivial example are the theory of Boolean algebras and the theory of Boolean rings. We all know that these theories are, in some sense, Boolean algebras and Boolean rings are just the same thing. Mutually interpretable tautological equivalence, another way of expressing that is to say that the two theories, in some sense, have the same models. And that means if you've got a model of one, you can, using the gadgetry of that model, define the gadgets with which you can decorate the carrier set to get a model of the other theory. And this is clearly the case with Boolean algebras and Boolean rings. You can define Boolean algebra operations in terms of the ring operations, and vice versa. A more recent and highly non-trivial and interesting example is a theorem of Richard Kay and Tim Lock Wong, which I've cited there. And that shows that Peano arithmetic is synonymous with this rather mucky-looking theory, ZF minus infinity plus the negation of infinity plus transitive containment. You need transitive containment as an extra axiom for technical reasons that we won't go into. Now, this synonymy of Peano arithmetic with this set theory, this is in virtue of the trick, quite an old trick, no, due to Ackermann, of Hilbert and Ackermann. You can define a membership relation between natural numbers. You say n is a member of m, as it were, if and only if the nth bit in the binary representation of m is set. If you think about it, this relation is actually extensional. It's extensional and it's well-founded, and it turns the natural numbers into V omega, the collection of hereditary finite sets. Now, there's a tweak to this due to Oswald, which will have an afterlife later on, so I thought I'd mention it now. So n is a member of m in this new sense if either m is even and the nth bit of m over 2 is set, or m is odd and the nth bit of m minus 1 over 2 is clear. As I said, this will come in useful later. Now, an even more recent example is a theorem of my Cambridge colleague Benedict Loewe in this paper which I mention here. And he says that ZF and ZFU, which is ZF weakened to allow Urelemente, are synonymous. I think there's a slight bug in this paper. I don't think he actually proves that ZF and ZFU are synonymous. He proves that ZF is synonymous with ZF allowing countably many atoms, but the construction is a good one. And what he does is show that if you start with a model of ZF, you can define a new membership relation such that when you decorate the carrier set of that model with that new membership relation, you get a model of ZFU, and vice versa. Now, why do we? Why am I interested in synonymy? As I was saying earlier, the thought is that if you have two synonymous theories, that they're in some sense reporting on the same mathematics, that the difference between them is a difference of presentation rather than a difference of mathematical substance. So, and there are sort of philosophical ramifications to this, really. I mean, you think of K. Wong that says that pure arithmetic and this suitable set theory are the same theory, are synonymous. The thought is that the noumena that they are describing are the same thing. So that they're a theory of an entity that can be either can look like either a natural number if you look at it with one pair of spectacles, or a set if you look at it with another kind of spectacles. Now, one question that has interested me for many years is whether the mathematics that New Foundations reports on is fundamentally different from the mathematics that ZF reports on. NF says there's a universal set and ZF says there isn't. But might this be just a presentational difference? Might it not be the case that they're really describing the same thing in the same way that Benedict's result says that ZF with Ur element and ZF without Ur element are actually, they're just two different ways of describing the same mathematics. In this connection, I want to bring up the work of Church, which I haven't itemized it here. In 1974, quite late in his life, Church published a paper about set theory with universal set. Church got interested in NF. He didn't do much with it, but a little bit. There's some manuscripts of his, which Princeton have let me show, and I'm transcribing them and writing commentary on them. Church, in the 1974 paper, Church gives a construction of a model of NF2. NF2 consists of the two stratifiable axioms of NF. Those are the axioms of NF that you can stratify using only two levels. And NF2 can actually be described as extensionality, complementation, existence of empty set, and binary unions and intersections. So the universe is a Boolean algebra under set inclusion. And Church gave this construction, which I've shown in front of you here, construction of models of NFU, starting from a model of, well, your favorite well-founded set theory. Let V be the universe of whatever model of your favorite set theory you're using, and you fix a bijection between the universe and a set of pairs of elements of the universe with flags. Think of these 0 and 1 as flags, and then you say these are flags, and then you say X is a member of Y in the new sense. These are X and Y members of the universe of ZF, whatever it is that you're working with. You say X is a member of Y in the new sense if either the second component of Y is 0 and X belongs to the first component, or the second component of K of Y is 1 and X does not belong to the first component. Clearly, this is going to give you it's not blindingly obvious that this is extensional, but actually it is. And what it actually gives you is a model of NF2 plus two axioms. The well-founded sets are a model of ZF, and every surjective image of a well-founded set is a set. Now, for some years, I tried, entirely without success, to get my PhD students to prove that this theory, NF2, this theory here, is synonymous with ZF, which I firmly believed it to be. And Tim Button, God bless him, has now actually done it. He has shown that this theory is synonymous with ZF. Now, I think this is a result that I think those of you who are interested in philosophy of set theory could usefully apply yourself to. I mean, if these two theories are synonymous, one of them says, sorry, they're synonymous and they're both set theories. This is not a situation like K1 where you have a set theory that's synonymous with an arithmetic. You have two set theories, competing set theories that are synonymous, and they contradict one another. One of them says that there's a universal set, and the other one says that there isn't. Now, what should our response to this be? An awful lot of set theory. Most people who call themselves set theorists believe that ZF or some modification thereof is, I hesitate to use the word true, but I think one has to use it. This is what people think. But then if ZF is synonymous with this theory of churches, and one of them says that there's a universal set and the other one doesn't, I think we have a problem. What is the correct way to describe this situation? Button, as I said, Tim has, I think, proved the synonymy result. He submitted it to the JSL, and they're going over it even as we speak. So Church's set theory is synonymous with ZF. What about NF? Now, Randall and I have recently, and we've sent this off to the JSL, we've been able to show that New Foundations is not synonymous with any theory of well-funded sets. Quite why this is so is not clear. I think it's obviously something to do with the fact that NF proves the existence of more sets than NF2 does. But what it does tell us is that the mathematics that NF is reporting on is different from the mathematics that ZF is reporting on. I mean, if you're an NFist like me, you would say, well, NF, of course, is reporting on more, because in NF, you can discuss the theory of well-founded sets in NF, and that, of course, is going to give you ZF. So NF is, in some sense, richer. I don't think that reflection would be well received by the ZFists, but I don't see why it shouldn't be. I think it's a point worth making, and certainly a point worth discussing. Now, recently, as a result of my communication with these gentlemen, Ali Inayat and Albert Visser, I've been exposed to the idea of tightness. A theory is tight if any two extensions of it that are synonymous are identical. Piano arithmetic is tight. ZF is tight. NF is not tight, but it is stratified tight, by which I mean if I have two stratified theories that are extensions of NF that are synonymous, then they are identical. Now, tightness is a relatively recent concept, and I'm sure there's a lot of work still to be done on it, but it does seem clear that it's something to do with second-order categoricity. As I say, PA is tight, and it's second-order categorical. ZF is tight, and it's not literally second-order categorical, but there's a weak sense in which it is second-order categorical, which we all know. Interestingly, and I think this is due to Ali Inayat, Zermelo is not tight, but Zermelo plus the levels exist, the ranks. You know, for any ordinal alpha, the set of things of rank alpha is a set. If you add that to Zermelo, you don't get the whole of ZF, but you do get a tight theory. I think probably I see I have already overrun. That might be a good point at which to stop.